Hey everyone! Welcome back to BugNoJutsu, the channel where we break down DSA problems with ninja clarity. Today's problem is a real brain twister. We're given a sequence of directions, and we're allowed to change up to K of them, but we want to end up as far away from the starting point as possible. Let's not just solve it, let's understand it deeply. You're given a string, S, where each character is a direction, N for north, S for south, E for east, W for west. You start at position 0, 0. With each character, you move one step in that direction, but you have a secret weapon. You're allowed to change the direction of up to K moves. That means at any step, you can replace the original direction with a different one, up to K times in total. Your goal is to figure out what is the maximum Manhattan distance you can reach from the origin after going through the string, using at most K changes. At first, it feels like you need to simulate every possible way of changing directions. And that would take exponential time. But here's the core insight. Each time you change a bad move, let's say you were going the wrong way, and fix it by changing the direction, you don't just save that one unit of movement. You actually gain 2 units in Manhattan distance, one that you recover from the bad move, and one that you gain from the correct move. So every direction change gives you a potential +2 boost in distance, but you can't travel more than the number of steps you've taken, right? So even though K changes could mathematically give you +2 multiplied by K in distance, we must cap that by how many steps we've actually made so far. Here's how we approach this smartly, without brute force. We start at x, y equals 0, 0. For every move, we update x or y, depending on the direction. After each move, we calculate the current Manhattan distance, abs of x plus abs of y. Then we add a theoretical boost, 2 times k, since we could change k bad directions. But remember, we've only made I+1 moves so far, so we cap that result using min. Throughout the loop, we keep tracking the maximum distance possible so far. This gives us an O of n time solution, with no need to explore all combinations.
This problem teaches us how to think smart when we have limits. Instead of trying every possible move, we find a shortcut by understanding the pattern. We learn that every change we make can boost our distance by 2. And we use that idea to get the best result with the fewest calculations. It's also a great example of how we can mix simple math and logic to solve what seems like a complex problem. So overall, it sharpens our greedy thinking, helps us understand grid-based problems, and teaches us how to write clean and optimized code.
And that's it! Instead of fixing direction conflicts manually, we turn the problem into a smart distance calculation, making the solution clean and efficient. If this helped you, like, share, and subscribe to BugNoJutsu for more daily insights and killer explanations. See you in the next one. And as always, keep debugging like a ninja.